mechanics of learning, which basically take us through how we learn when we talk about machine learning, I mean deep learning. So what is learning? How do we learn? So that's what this chapter is all about. Let us understand how the process of learning, and finally it uses Pytorch to automate this process of learning. So today's this chapter is going to be three different sections. The first one is parameter estimation, which will go through manually and boring, and we'll go to the next one, which is optimizers and add autograd. So autograd is something in Pytorch that allows you to automate this process of learning, and we'll see what is called optimizer. So we have 3 notebooks in the chapter, but the first one, as I said, that we will use to show how learning works manually is boring. So it is fine. It is fine if we don't understand the first process. That is the manual way of understanding how deep learning works. In the next step, that is using Pytorch autograd, it will abstract all the process of learning. So you don't need to learn if you are not familiar with differentiation and derivative and stuff like that. So when we come to this section where we will be using what is called Pytorch autograd, then you'll be fine. So just a housekeeping that this first session is boring, and it just lays a foundation going to the next step. So let's get started. So this chapter basically starts with the first thing, which is called explain how modeling works. So they said a timeless lesson in modeling. So they gave an history on how Kepler's tried to find the laws of motion using some steps. So what he does basically over centuries, right? So what he does basically is what we are familiar with machine learning approach. He got a lot of data and try to visualize the data. Yeah, of course, that is what we do, right? When you get some data, you try to visualize the data to see if there is any relationship that you can model. If the data there isn't any relationship, then you don't even waste your time, right, to try to model the data. Now, he chooses the simplest. Then when you see that there is a relationship in your data, then you can choose a modeling algorithm, right? So you choose a modeling algorithm, but he does not actually use the whole data. He split the data so that he can do the training experiment on one side. After you finish, then you can evaluate on what is called validation set. And now he iterate all this process of training. So yeah, iterate and now validate on the final. So and now, yeah, so this is something over centuries. They gave a history. So what is this is saying that history of science is basically constructed on these steps. So it is not now deep learning work. So even in other fields like weight science, what do they call weight science? They do this how experiment works. You try it, it fails. You try, you change this parameter, you change this until you get some kind of optimal solution. When we say optimal, meaning that it is not perfect, but it's reasonable to go through with that solution. So that's how science works. Now, the good thing is Pytorch automate all these steps, so you don't need to bother yourself on how can I change this parameter. So there is a lot of function like optimizers in Pytorch that really do this well, that you don't need to bother yourself. In fact, there is some kind of stuff like going to the loop and other stuff. So Pytorch all do this kind of steps. So that's the essence of what we are using Pytorch to abstract this. So let's go to the first step. Learning is just parameter estimation. So what they try to start with this chapter is that they discuss about the concept of when we say we are learning, deep learning, what we are machine learning or deep learning whatsoever, what we are basically doing is we are doing what is called parameter estimation. Basically, it's just trying to find some parameters that optimize your loss function, right? So you are trying to find some parameters that minimize the loss. That is just what is deep learning. At the end of the day, when we train a model from the beginning to the end, what we are interested in is just to find some parameters that when we flog them, the loss is low. That is, as you said, learning is just parameter optimization, parameter estimation. So let's look at what they mean. So let's assume this, you have an input here, right? And you have a ground truth here. This is your input ground truth, right? So what we want to do is we want to build a model that, given this, I don't know, my mouse is showing the stuff in the, do you see my mouse showing the stuff?
Yes.
Okay, so what is saying is that we have input and we have output. So we want to find a model, some weight that when we do prediction, this, can you see is yellow? It gives us this. This will give us this, because this is the ground truth. They give us this color, and this will give us this color. This will give us this color. This guy will give us this color. You know, so this is the input. We have 1, 2, 3, whatsoever. I think 10. This item. So it means we map each one to is this one. Now, how can we do this? This is where the learning starts. Now we give our input, and now we pass through some function, which are mathematical functions, which we call neural networks or some kind of stuff. And now we have the prediction. Look at this. This is the ground truth, but this is the prediction. Ground truth, we expect to have this if we have perfect prediction. But remember, we cannot have perfect prediction, right? Now, so let's assume this is our actual output, what we have the prediction. Then we can see, okay, now let's look at it. Now you can see the first one, it gives us this color is not the ground truth, right? So here we are wrong, right? We are wrong. What about this one here? Yes, of course, this is the ground truth. We are correct. What about the next one? Is yellow? Yes, we are yellow. It's yellow. Okay, let's. What about this? Is this? Yeah, here is correct. This one, can you see? It's yellow, but it gives us this color. So this is a prediction, but this is the correct one. So we're supposed to have, given input, we want to have the prediction here to be the same as this. But you can see we have some errors, right? So this means that we use some model here, some function to get the output, but we want to change some stuff here so that this will look like this. That is what we have, what we call, we calculate what is called error. So from here, input to the output is what we call forward pass. That is, given some input, you generate some prediction. This is a prediction. But this prediction, there are some incorrect results, as we can see. Then we need to correct this result. That is where we go back and correct some weights here, what we put. So going back is what we call back propagation. And now we change some parameters here and try to see what is the output. If the output may be as mun gyara wasu, then if bai bamu the sum in one number, we change another parameters, we iterate. So you can see this is iteration. This means that this process is iterable process. You keep iterating this one, you tune some stuff until it gives you something exactly this, the ground truth, or something similar, not exactly. Now, this is basically what is called the learning process. And after you finish this training, you may not have train your old data. You can divide your trainer. This is the training data. This is the validation data, some stuff like that. So you can do some stuff like that. So this is the mental model of how learning works. Anyone want to add something, any question about the mental model? Any question, or someone going to ask something? Okay, so if there is no question, we can move on. So we can see here that basically what we are doing is here we update some weight. So I like this figure because it's yeah. So you can see here, this is what we are saying. It's the sum with this. It's the same with this, but this one I like it more. So you can see that this is the input, and this is the forward pass. You are going this through this way, some transformation, which are mathematical function. Then you make prediction. Now, when you make prediction, this is your original target. Now, what you can do is, now this is the prediction, this is the target. But comparing the prediction and target, you find out there is some error. So this error, we use some what we call loss function to find the loss code, the error. Now, okay, this is the error. How can we update this error so that our next prediction will be small? So we use what we call, we change the weights here. We change some weight if we use, for example, the weight is 0.1 or whatsoever, we update it and we go through again. It changes weight. So that's why this process is repeated until we have the minimal loss score. So this is basically the mental model on how learning works. Nothing much. We are just trying to find the best parameters, these weights. So at the end of the day, we may have parameters, these weights, that when we input into our model, we have a very low score. So when you train a deep learning, at the end of the day, after you are training, what you will have are some parameters, some weights that actually minimize the loss. Yep. So any question before we move on? Any question? Or somebody wanna add something? All right. So as I said previously, today's section we have in this section we have 3 sections. We have this first section that I'm working on, which I said is really boring in the sense that it tries to explain from the beginning how learning works. But it is fine if you don't understand if I will go. But when we go to the next section, which you use in Pytorch, it actually abstract everything. But just to keep in touch that this will be boring at the end. So let's look at a toy problem to see how learning works. So let's build a model and see how this learning works. So let's construct a data set. Assume you have a perfect thermometer, but it does not show a unit. So for example, you have a perfect thermometer. This is a reading, right? This is a reading, but it does not show unit. But we know that the unit, we have some unit in the temperature. This unit, this is the value in Celsius. This is the value in Celsius. So for example, what we are trying to say is that assume this is the value and this is the ground truth, right? So corresponding, what do you call it? The corresponding ground truth. So we want to make predictions, something like that. So let's assume we have 2 values here. Let's look at the type of this. We can see basically this is basically a list, right? This is also a list, but we want to construct them into a tensor. We know this is how we can change these guys to tensor, right? So let's change this guy to tensor. Yeah, so this is the temperature in Celsius and temperature in unknown unit, right? So this is the unknown unit, this is in Celsius. So we all know that now here this guy is in touch, right? In tensor, it is in tensor format. So now we define our input, the data we're going to use. So we all know that when you want to do deep learning or whatsoever, or data science whatsoever, we can actually try to plot our data, as I said, and that's what Kepler's. We already outlined the step. Got a lot of data. So the first thing is, if you want to do, get the latest data. The second step is what? Visualize the data to see if there is any relationship. And the third is pick a model. So now we generate a data that we want to do prediction. Given this, we want to predict this. Given this, we want to predict this. Now, we get the data. Let's visualize it. We visualize the data here. Right? So this is visualization of the data. But we can see here the data that is noisy because it's not like perfect. It's not cluster, right? Because you can see some data is here and here. So there is some kind of noisy. And we will never have, in some sense, our data to be perfect, right? So, data is somehow noisy in some situations. So we should not always expect our data to be perfect. So what do we mean by when we say the data is noisy? I have some graph here to show the data that is not noisy, like some example here. So if you look at this one, this you can see here, this is an example of when you have the data you can see is noisy, this is not noisy. So a noise data is basically there is some kind of variability in it. So the natural measurement of data is noisy. So we can see that this is our noisy data. So now we think that we can model this relationship between the temperature, the measurement, and the temperature in Celsius. We can model the relationship using maybe linear model, right? Because you can see, we remember our linear stuff we can model this linear model. So the next step from Kepler's is to do what? To choose a model. Now, what kind of model we're gonna choose? So you can see here, got a lot of data, visualize the data, choose a simplest possible model. And now, so let's choose a model. Yeah, so let's do the model. So how can we build a model here? We can use a linear model. So a linear model is something like this, right? If you want to see this temperature in Celsius, we can use something weight times temperature in unit plus bias. So this is something that we know in our what do we call it in our mathematics? Y is equals to mx plus c. If you want to model a linear relationship, we say let's assume the simplest possible model for combating between the two set is linear model. So we do assumption that the relationship between this guy and this guy is linear model. So what is linear model? If this T and this are linear, then we can express them in this format where W and B are the weight and parameter and bias. So what is weight? So weight is something that, as I showed, that we can keep collaborating here. This is a weight, right? So when we keep collaborating the weight, we try to change to see that our loss decrease. So that is what is weight. And yeah, so we have what is called also bias. Maybe we may not see it here. Yeah, so right. So if this is our linear relationship, we need to estimate this W and T. We need to estimate W and T, that is the weight, and B to find a best possible solution. Let me just see introduce something that where is this guy? Okay, let me show us some kind of hypothetical example. Right. Where is this guy? Just give me a second. Okay, just give me a second. I have something to show. Okay, this is it. Where is my? Okay, yes. Okay. Can you see my screen now? Can you see my browser?
Yes.
Okay, so let's assume we have a linear relationship. You can see this is linear relationship, right? We have X and Y, right? This is X and Y. So if X is 1, Y is 2. X is 1, Y is X. Can you see that? Y is 2. If X is 2, Y is 3. X is 2, Y is 3. Can you see that? So this is a linear relationship, right? Now, what we want to see here is that how can we express this relationship? This is Y equals MX plus B, right? So if Y is equals MX plus B, then how can we perfectly pick a line this? So we can see we have some parameters B and M, which you can see B and M. The relationship is Y equals MX, but we have this. So when we tune this parameter, can you see B? Can you see the model is not on the line, right? When we model this, look at it. Can you see the gradient, how it is? Can you see the gradient? Can you see the gradient, how it working? Can you see the gradient? Can you see? So our job now, what we want to do is we need to tune B and M. That is, we need to tune the bias B and M gradient so that the model perfectly this. Now, how can we do that? We keep changing the values, we keep changing the values. So this is the idea of this one here as well. This is the idea here. We keep changing the value W and B until the model fits the line, right? We keep so that's the idea also here in neural network. This way, you keep changing them. If there is error. So in this case here, you can see that there is error. It does not fit this line, right? So we change, okay, we change this one. Okay, no, maybe we can tilt this one. Can you see we tilt this one somewhere here? We tilt it this somewhere here. Or we can go this one here. We can go this one here. Yes, something like this. Okay, so we tilt it this way. Now, you see, there is an error. Still it doesn't fit this way. So it's okay, let me change another part. So here we are, the parameters, we have weight and bias as well. Not only weight, we have the parameters. Both the parameter will be changing them into a model. So now how can we perfectly tune this one? So maybe you can see here, can you see when I put 0.8, but still here it doesn't fit. But my gradient is, let me change my gradient to 1. Can you see the gradient change to 1? It fit. Let me change the B to 1. Maybe 1. Okay, you can see now we have B equals 1, M equals 1. Can we see we fit the model perfectly? So when you are doing learning, in this case, we give an example. But remember, this is a toy problem. We are not using the neural network. in the next chapter, we use the neural net, but here just to give intuition how learning works. So we are using linear relationship, which is this. So in essence, when you say you are learning, we are trying to find these parameters P and M. That is the gradient. M, ita ake kira gradient. If M, you can see is the gradient, right? And the bias. So when we say we are learning, we are trying to optimize this one. Let me see. Can you see when I put this guy? You can see automatic. Let me put this guy. Let me put that guy. Can you see they are trying to automatically, they can try. Can you see? So we don't know at the first instant which one will work best. So this is really, really iterative process that we need to tune and try to see we actually have a perfect result that tuned the result. So this is what is basically trying to do. So we model this to something like this. Yeah. So you can see basically we are nudging W and B. Here we are nudging the W and B. We nudge them in some direction. Can you see that? We nudge them in the direction. Can you see them? And try to fit them. So that's basically the idea of how learning works. Yeah. Anyone want to add something or any question? Anyone want to add something or any question? Oh, I'm afraid this today lesson, maybe we may actually go overboard, maybe up to an hour. Okay, so let's go on. So now you can see here, now we actually know how the learning works, but how do we know that and we are not actually doing correct? So we know now we need to change W and B to fit the model. So if we change W and B, example here, I change here, I change this one. This does not fit the line, right? How can I measure that I have not fit the model perfectly? How can I know that the model fit perfectly? For example, I have one something like this. Okay, this is this guy. When I have this fit, how do I know that I fit perfectly? How do I know I don't fit perfectly? Then we need to an error, a measure that there is an error. So we need to measure what we call a loss. So loss is what we need. So here, this is what they discuss. So a loss function is a function that computes a single numerical value that learning program will attempt to optimize. So here, when we do the prediction, this is a true target. Then we have what is called loss function that try to find the difference between one and one to find the loss. So let me, I always try to do go through graphically to see the intuitive way. I just have a copy another example from the internet for us to see how loss works. So let's assume here, I'm just giving an example. We have some data, we have the age, we have what is called affordability. These are some of our value, and we want to predict, given age and we want to predict if there is insurance. If insurance is this is what we want to predict, right? So this will be our values. So here, for example, I have my input. So here, look at it. Here we have what we call W times T plus B, right? W times C plus B. So meaning that here I have more than one value. So here you can see I have Y equals W1 times X1, W2 times X2. So W1, W2 are weight, but X1 and X2, because I have two things, right? If I have only one, I can have X1, then plus bias. Can you see I have plus bias? So this is the same example I want to, the same what we saw, but here I have two input. So now how can we show, I want to show us how, what we mean by loss. So this, we have two input, affordability and this. Now we input into our model, Y equals to W times X1. What is our X1, which is age? What is our X2, which is affordability? But W1 and W2 are constant value that we need to change, iterate. So as I show you here, this value, which is W, B is the gradient, and B is the intercept, and M1 is the gradient. M here is the W, here, which is the gradient. Can you see MX is the W, but this is bias. So we need to put some constant. W and B are some constant. So you can see here we have W1 is 1. Age, we put the value of age here. So if we are talking about, for example, if we are talking about this one, the age, this is the value, and W2 is also a constant, and this also affordability. Age will be now 22, affordability will be 1, and plus bias is 0. Can you see that? So this is just a simple expression. Now, this one, we don't come to it, but just assume that here we calculate the Y, and now we have what is called activation function. So the result of the Y Now we use what we call activation function, and the result gives us 0.99. So you can see that the prediction now is 0.99, but the actual result is 0, right? So we need to calculate some error. So error is absolute error, is the true result minus the prediction. So it means we said true result, which is y, minus prediction, so which is 0.99. So here, this is how we calculate the error. So we go, if we have n number of points, we go this one again, we calculate the error on this point. So we said, okay, what is the age? We calculate here, and also we have this. We also, if we have another up to the last value, we calculate and now find, you can see here where we do the prediction is equals to 0.99, but the actual value is 1, right? So we find the absolute, that is 1 minus 0.99. So you can see we have many errors at this point. So what we can do, we total the errors, that is error plus error from error 1 to error last error. This individual one is called the loss, Now, but we need a single error, so we need to take them all and find the mean. So because we have n number of errors, we need to calculate them absolute error, mean absolute error. So this is what we call cost function. So this is what we are saying here. Can you see cost function, right? Or we call them lost function, something like that, right? And this is a score. So this is the final score here that we calculated. So there we have different kind of loss function, cost function. We have absolute error, and we have mean square error. So it depends on two scenarios. You can use any one you wish, but just bear in your mind that in classification, we usually use what is called cross entropy, and a mean square error we use for regression problem. So that is basically how we calculate the error. Remember, what we are saying is that we have a model, and we have some parameters, weight, that we want to optimize, but we don't know when we go wrong. How can we know we go wrong? That is, we need to calculate an error. Now, calculating the error, that is what we define here. And this is what I give an example how to calculate the error. You can calculate for each point the error, and now you sum them up at the end, and you have what you call cost function. Right. So that's how we calculate the error. Any question before we go
on? Excuse me, doctor.
Yes.
I don't know, is there any notion behind choosing the values of W and B?
Exactly, yes. So this is a good question. So Dr. She is asking, do we just choose W and B? That is the weight. Do we just initialize them? This is different, another concept that we will learn, initializing your parameters. So there is best way to initialize these parameters, but for now, let's assume that we just initialize them randomly, because we are not start training neural network here. We are just using just conceptually trying to understand how it works. But the short answer is yes, there is best way to initialize your parameters that they can learn best. Because like if you initialize your parameter first 1 million to 1 million, you can see the best value here is 1, right? That fit the model as our stuff, right? But when you initialize your parameter randomly to 1 million, how can you come over to 1? So there is, there is yeah. Okay, yeah. So that's how the loss is calculated. Any question or addition? Anyone want to add something before we move on? Any addition? Any addition? Ya kwai ali nake ta turanci ne. It's just group discussion pa.
So what basically what we are doing is,
okay.
Is all encompassing. But my question here is with regards to the previous, is it the previous diagram that calculates the error? What is that Z?
Beware. This one?
Yeah,
okay, this one?
Z is equal to 1 all over 1.
Right. So here we don't introduce the notion, because even in the chapter they don't introduce the notion. So what is happening is that calculating this y, which is basically the prediction, y equals this. This is a linear function, right? This is a linear. This means that there won't be any change. So there is what we call activation function that actually change this linearity format. It change this one from to non-linear. I don't want to talk it so that I may not introduce more conflicts or to confuse, because even the chapter I don't introduce it. But the idea is this: when you calculate your prediction, that is y equals to this plus this plus this plus bias, that is not the final prediction. You need some ways to bring this prediction to some that is within the particular range, 0 to 1 or whatsoever, so that you can be able to change this from linear to some complex model. So we have many stuff that are called activation functions. So after you do this summation, then you supply this your y to this activation function. So here you can see z is activation function is called 1 over 1 plus e exponential y. So we have different kind of activation functions, such as who can remember me?
Sigmoid.
Sigmoid, Tanyage, Relu, yeah, wow, rectify, all these those stuff. So can hyperbolic, so all these one are the activation functions. They are not linear. They are non linear. So, but this you can see is linear relationship, right? Because this is just a linear, right? Because this is linear and it does not make any relationship more complex. So we need to change this linear notion to yeah. So I don't know if anyone, Idris, you want to add something on that, top of that? Or anyone? Okay, any question or anybody want to add something? Please, let's contribute. Let's yeah, when a discussion it makes sense. Yeah, anyone want to add something? Okay, please, if you want to add something, feel free to add so that we can learn together better. Yeah, yeah.
And I think other than the fact that z equals to 1 over 1 plus exponential minus y, it's the formula for this sigmoid function, activation function. So, you know, it's not stated there, but just in case we want to distinguish between the other kinds of activation functions. So that's formula z equals to 1 over 1 plus exponential minus y is the formula for sigmoid activation. Yeah. So just to add what Tunde says, that's why I didn't even introduce this concept, but I just copied it. I want to introduce. So to change from linearity to nonlinear, we have different activation function, as we said, and they have different formulas. So let's see this. So maybe activation functions formulas. So let's look at them here. Yeah. So you can see these guys. So you can see we have, maybe this one. Yeah. So you can see these are the activation functions. So we have many of them. This will be introduced in the next chapter, chapter 6. I just yeah. So this you can see we have this is linear. Can you see them? So sigmoid. This is sigmoid. Here, so you have different formula, ReLU, and they have their advantages and disadvantages, but we are not here to discuss that. Will be in the next session. Yeah, thank you, Tunde. Anyone want to add something?
I may add a bit of information. I don't know how important it is.
Yes.
Generally, we use the activation function to smooth our values. Because when you are doing mathematical computations, your values can easily shoot, so that your weight and your bias may have a very big variation, making one very insignificant or thereabout. So you use your activation function to keep them within boundaries, depending on the activation function between, for example, 0 and 1 or minus 1 and 1. Whatever you get falls within that range, so that some of your parameters do not outshine the others. One may be very small and the other very big, make it as you are doing your back propagation very insignificant. Yeah. So I don't know if that's the case.
Yeah. So that makes sense. So what we are saying here still is telling out importance of activation functions. They try to put prediction in some range, whether 0 to 1. There are a lot of notion we can come to that. So let's move on. So from problem back to Pytorch. So now we have seen how to formulate the problem. We can actually do that. So we figure out our model. great linear model. We figure out loss function. Now we have seen how can we start learning. So now we figure out this loss function. We figure out this way. So we figure out this model. We choose a model, right? Which model? We choose a linear model. We choose a loss function. We know how to choose a loss function. But how can we start the learning process? So that is a good question. Now, so let's remember we create our points, the tensors here, right? We create these guys. And so let's write the model. So the model is this. Given this guy, TU, which is the input, the data, and given the weight and given the bias, so given the model TU, given the weight, given the bias, we create a function, it returns this guy, this times this plus b. So this is the model, right? This is a model. This is our model, right? We implement it in Python here. How can we implement our loss? What we do in loss, basically, as you can see, the loss, as I said previously, is we try to find the mean square error of the sum of them, right? You can see we have them 1, 2, 3 up to n, right? But what we can do, we do the summation from 1 to n, taking the absolute value. We need the difference to always be positive, so that's why we take the absolute value. Yeah, so we can see when we take them, but because we take n of them, we need to take the mean of them, right? So that's why we say divide 1 or divide by 1 from 1 to n, taking the absolute value. So you can see here, how can we replace that? We can say, okay, given the prediction and given the TC, which is the degree in, what is that? Okay, this is the problem, values in Celsius, right? And this is the value TU, which we plug here. And this is the result. This is the prediction, right? This is the prediction. So we give this guy, and this is the prediction. Now, this means that for our loss, what do we do? We said, given the prediction, we subtract from the what? From the what do you call ground truth, right? So you can see this is given the prediction and given the ground truth, the in Celsius, we find the square difference. Can you see TP minus TC times 2? This is square. Can you see? And now we return the square difference. Can you see square difference dot mean? Because we are taking the mean here. We are taking the, this is what, can you see, we are divided by n, which is the mean. So basically we are saying the prediction minus the ground truth minus prediction divided by n. So here we implement it. So here is our loss. So this means that we implement our model, which is forward pass, and we implement our loss, which is the square, mean square. I don't know if anyone want a question or question. Any question? Okay, so let's initialize our parameters. So now we define our model, we define our loss. Now this way, we define our model, we define our loss, right? Let's initialize what and wait. Just use some random values and now make some prediction. Let's look at it. So let's initialize the weight. So you can see we said touch that once and touch that 0. So we use ones and zeros randomly. As Malama asked, how do we wait and how do we initialize this value? So we initialize them here randomly, and now we can run them. So when we initialize them, we can now call our model TU given W. So now we have our W, we have our B. So since we have now our weight, we initialize our weight and bias. We have our input, which is X, and we define the model. We can make prediction. So what is our this is our model. We define it, right? And this is the input. This is the weights, weight and B, and it returns the result. And this is the loss. So let's look at it. So here you can see we initialize the weights and we invoke the model here, right? Because since we define the model, it takes some argument TU and B, and now here. So this is our prediction, right? Now, how can we calculate the loss? So for us to calculate the loss, what loss take? The loss take the result of the model, that is the output of the model, and now subtract with the ground truth, right? So here, this is the result. Yeah, of course, then we train our model, but we can see here the value of the weight here. The value here, we can see the error is large because this is a loss, right? The error is large. We randomly initialize the parameters. So Malama, you can see that what we are saying, your question is, how can we initialize the parameters? So
Yes.
we initialize the parameter anyhow. Let's assume we do it. You can see the error is very large here. right?
Yes.
Because we have not intelligently initialized our error. Because we know how intelligently we can initialize error, maybe small. You can see that it can try to perfectly fit the model, right? It can try to perfectly fit the model. So it means we need to find a better way to initialize our parameters. So here you can see the error is very large. So we implement the model at loss. How do we estimate W and B such that the loss reach minimum? So this is a next natural question. How do we estimate W and B such that the loss reach minimum? So the question is, how do we estimate? How can we find best value of B and me so that the error is very small? Yeah, so that's the next question. And yeah, so for us to do that, we will work thing out by hand and then learn how patches. So this is the boring part of it. They will try to show us how we can optimize this W, B and M, which has W and B, so that we perfectly fit the model. But down the line here, they will try to explain it manually, which is boring. But in the next session, we'll see how Pytorch, Autograd, abstract this thing, do it easily without any hitches. So any question before we move on to the next stage? Or anyone want to add something? Please add. I remind you, this is discussion. We learn best if we have contribution. Yes. You want to add something on top of this?
Yes, I have a question.
So,
yes, I have.
Okay.
My question is, when calculating the error, does interchanging the predicted value with subtracting from predicted value from the true value have an effect? Because sometimes we can have negative value. So when we have maybe -1, -2, we get -3. Then when we put it to ABS function, we get 3. But when we interchange, when we have maybe -1, -2, we get 1. And when we put it to the ABS function, absolute value function, we get 1. So does it have an effect when we interchange the true value with the actual with the predicted value when estimating the
I see what you mean. Okay,
yes,
that's a good question. So Falalu, what he's saying is this: instead for us to say, okay, this is the predicted value, right, and this is the true value, instead for us to say true value minus predicted value to give us 0.01, can we interchange saying predicted value minus this guy? So predicted value here 0.99 minus 1 will give us minus 0.01, right? Which taking the absolute value will give us 0.01. But Falalu, what I think Falalu you are saying is, assume we have our prediction is minus 0.2, right? And can you say your example, please?
Okay. Hey, let's assume that we have true value is -1, and our predicted value is -4.
Okay, to Bashi. So predicted value is -4 and true value is -1. So when we say that, we can say okay, -1 minus it will give us -3. And the absolute value of -3 will give us 3. But in another way, when we say
-4, it will be -1 minus -4,
which will give us plus
3. It will give us
the other
3.
way, kuma make subtraction zai bamu what?
The other way around is
-4.
Hello, good morning. I think
yes.
That will give us -4 minus 2, which will give us -5, right?
Yes.
Okay. Right. So
hello, sir. If I can come in.
Hello. Yes.
Yes.
Yes. I think the function is designed in such a way that the output will not be more than 1. The output is always between 0 and 1.
Okay.
This is a classification like as you started, it's a linear logistic regression. So the output is either 1 or 0.
Okay.
It's either 1 or 0. So your predicted output is always between 0 and 1. So if the actual output is 1 and your predicted value is between 0 and 1, so you are definitely going to get less than 1. Yes.
Yeah.
Okay. So what about our activation functions, like the ones that I showed, let me see that. Okay, these are activation functions. I think if we go through them, we can learn better, because if you look at them here, for example, this ReLU, look at the result is can you see it's 0 and 1, right? What about this parametric ReLU is 0 and 1, right? So I think I'm not quite sure, as Said explained, I think the results, as if we applied our activation function, it changes the our prediction will be within those range. Yeah, so I think I don't have explained perfectly. I don't have the better answer. Yeah, maybe we can check, but if anyone also had anything to add, you can. Yeah.
For the sigmoid, I know that whatever number you give,
and also, sir,
to sigmoid, it will convert it. Okay.
Yes, this Z is equal to 1 all over something. Since you have 1 all over something, whatever you are going to have is not going to be more than 1. Because 1 all over something is going to give you 0.
Yeah, that's the sigmoid.
This is for the
it
sigmoid,
depends, but it depends. Yeah, it depends on the activation function you are using. But what I think we can generalize in all cases. So even if for ReLU, we can see that the output, I think, is 0 and 1. You can see for this parametric is 0 to 1. So for this case sigmoid, you can see it because it's 1 over this. Of course, it's 1, right? It within it cannot. But for TH, I don't know. But ReLU, I think is still valid. What Said said for this is still valid. But yeah. Okay. Anyone want to ask something?
Okay, what I want to add is for our features in machine learning or in AI generally, our features are mostly represented as non-negative values. You rarely see your features being represented with negative values. But just in case you have features that are represented in negative values, just like the illustration they
but
gave,
it's not a feature, it's a target. What he's saying is a target.
Okay, so whatever value we have, no matter how negative both of them are, even if the targets and the predictions are negative, you will always have your absolute function canceling out the signs. Like his question was in that error part, like what if you change the values, the position of the values? When he said -1 and -4, both of them, when you do -1 -4, it will give you +3. If you interchange it and you do -4 -1, it will give you -3. So anytime you interchange your values, it will always give you plus or minus.
No, I think
so there is problem,
but it will not give us the so the first case when you have -1 -4, it will give us +3, right? What about the other case? -4 minus
-1. It will give us
-3.
But the problem is
taking the absolute,
sometimes you may get a mix up with positive and negative value. Sometimes you may get a negative value for the target and positive value for the predicted. So that's where the problem comes in.
I think we can discuss this one when we come to
and also, sir.
Yes.
This is just a cross entropy way of handling error. I think you have other means of handling error like categorical cross entropy.
Yeah, so I think let's move on with I definitely don't know because like yeah. So let's move
on.
Doctor,
I think before you move on, I think one thing that I may add here is, sorry, I've not been contributing, is what we really want to find is the actual distance between the error or the predicted value and the ground truth. So if you have a ground truth of -1 and your predicted value of -3, so the actual distance between those is just a shift of 2. So you are not interested basically in the number that you are getting, but the amount of shift that you do from one value of the predicted to go to the ground truth. So most of these numbers we can see here, how about if we manipulate this, how about if we manipulate that? But I think basically the main idea is, because if we are introducing absolute value, we are not caring about either we are shifting to the right or shifting to the left, meaning shifting to the right whether we are adding, or shifting to the left whether we are subtracting. So we are actually finding the distance between the actual truth and the predicted value. So maybe we can go and do some maybe individual experiments to determine these scenarios that will likely come up, and maybe in our next presentation we see that, to save time.
Okay, so let's move on. I think we discussed this a lot. Maybe we can discuss like that. So I think even in the book they made mention this. We need our error to be positive in all ways. That is why we take the absolute. So let's see now. As I said, how can we actually how do you estimate W and B? So they give something like this. Given like we have optimizers, which we have W and B. We actually tune this optimized parameter W and B so that our model land best. So just the same example that I give here, where you can see we tune our parameters here, which is these guys, we tune them, and now until we have a perfect result like this, until we have this, it aligns. So this perfect result, so we are trying to tune this. So this is how we down along the gradient. So you can see what we mean here. M is the gradient, right? We need to find which direction we need to go to actually make our model land better. So how can we do that? There is an algorithm that do that using what is called gradient descent. So we will optimize the loss function with respect to the parameters. So we will optimize the loss function with respect to the parameters using what we call gradient descent. It's actually a very simple idea. That actually optimize, try to find out what are the smallest values for our W and B is gradient descent. So right, trying to find H in something and there is a change in something. So this means that when we use gradient descent, what we want to use is just to find the rate of change. Right. So as I said, this is a little bit mathy in the sense that there is a notion of calculus. Yeah. So this, yeah. I like to explain with graph. So let's assume this is our initial weight, right? Now, how can we actually change this initial weight? And let's assume this is our initial weight. It's large. The error is very high. This means that we need to come back and update this weight. So how can we update this weight? We use what is called gradient descent algorithm. So what does gradient descent? In a nutshell, because we are not here to discuss the gradient descent in a nutshell, we calculate the gradient at this weight, and now we use the previous weight minus what is called learning rate here, which actually determine how fast, how fast are we going from here, we jump to here. Can you see that? Or are we jumping from how large we jump? So we find the gradient at this point, and this gradient will determine the direction we go. We go opposite to the direction of the loss. So this is basically what we do, which is basically we said, okay, this guy minus learning rate times this, and this is basically the idea on how you can keep iterating or changing your weight. This is what we call gradient descent algorithm. Yeah, so you can see this is the implementation of the gradient descent algorithm. As I said, this is a little bit messy. When we come to the next session, we'll see how Pytorch abstract this. It is fine if you don't understand this. So yeah, we have what is called learning rate, which basically tell us how fast we move. So this is a learning rate, and we need to change our parameter W. How can we do that? We say W minus learning rate times loss rate of change, which is this rate of change. Can you see that? So here you can see we change our W, and we need to do the same thing with the P, which is bias, because we are changing the two parameters. That is the learning, the weight and bias, because we have two parameters. So we change them. So here you can see that. So if that is the case, now we can go back and update our W and P, right? Let me go. Yep. So this is what we said, calculating the loss now. You remember here, this is the way we calculate the loss previously. Let me show us. Can you see how we calculate the loss, right? The normal loss.
Yes.
Given this prediction, the ground. But now we have what you call the derivative. We need to change the formula for the loss. So how can we that? So the loss with respect to the weight, the change of with respect to the weight is given by this formula. Can you see that? Yeah, in the book you can see that with respect to the parameter and with respect to the weight here. So so here we have the original loss formula, but here we have the loss with the derivative. Can you see that D loss? This is just a loss. This is the derivative loss. We can see here, because here you can see we have this minus this squared. So if you are finding the derivative, remember if we have something squared will come back here. How can we calculate differentiation dy dy? So you can see that 1 and 2 in Tadanam, and we do the division. So this, as I said, is a little bit messy. Don't bother if you don't understand it, but this is just to give us an idea that what is happening. So here we find our the loss, but with derivative. So here it means we find we need to find the loss with respect to our weight, which is this is a loss with respect to this weight. So here, right? So let's now calculate the again the model with this new loss function. So remember, this is our model, the original model, and now let's calculate the model, but with the derivative. Therefore, D model with derivative. Remember here, if we have this W times C plus UB, P is a constant. So if we have this guy, Y equals to MX plus B, if we want to find the derivative of this guy, what will remain? If we want to find the derivative with if we want to find the derivative with respect to X, Y with respect to X, what will be the result of this? It will be only what? X, only what? Who can tell us if you want to find the derivative of Y with respect to X?
I think if X has the power of 1, what remains is M only.
Yeah, Y, exactly. Okay, so yeah, general equation. So X has a power of 1. Remember, B is constant. So here, this is our model. Remember, given this value, the input, given the weight, given the W, this is W times T, which is like M times X plus B. So we want to find the derivative of the model. So this is the derivative of the model. It will only left us with what? W, right? With the TU, right? Because yeah, this is the TU. Can you see that? So this is the derivative of the model, and the derivative of the with respect to this is the derivative to the model with respect to the weight, but the derivative of the model with respect to the constant. So we with respect to the constant, this will give us what? Only 1, because here you can see with respect to the B, given these guys, this will become 0. We have only our constant. So this is something that is implemented, as I said, manually, and it's bit some kind of mathy. But the main idea is this. If you don't understand this, it's fine. In the next session, we'll understand what this really means. The main idea is this. We need to find the derivative of our points, the derivative of this point, and try to find which direction we're going to move. That is the gradient, and this is a formula, and this is what we are trying to implement here. But we are not going to, you will not be using this in the future. What we'll be using is what I will show next. It's just trying to show us the what is going under the hood. And if you want to do find the derivative, you implement it in this way. You find this stuff with the loss with weight, the derivative with the loss, and the derivative with the with respect to your constant value, and now you return this value at the end. So this is basically the idea that it explains how to do that. And when you want to iterate the models, we want to do so. This is basically we define a single way to for a single value. But when we want to do a model, we want to do iteration. This is how we do. So let's understand this. Now, if we want to do a training loop, what we need to do, we have a lot of things to consider. We need to give the number of epochs. That is how many loop you are going to do, the learning rate, the parameters, and your input parameter. That is the target and the values you have. So here we can see for epochs, that is the number of iteration in this range, 1 to n plus 1. The parameters you have, you give them to W and B, which are our parameters. You calculate the model. Then you see our model given the input. You calculate the loss. Remember, these are the steps we need to do. Let me go back. Remember, this is the step we need to do. Given the input, right? You have the weight. Let me copy this thing and go it there and explain it better. Okay. Okay. So if we have the input X, we have our function, we have our weight. So this is the this number of epoch, meaning how many are you going to do the iteration? How many times are you going to iterate? 1, 2, 3, 4, 4. That is the number of epoch. Learning rate, which is basically tell us how we are going to change the weights, how fast, and the parameters, which is the weight, and the TU and TC, basically they are the ground, the input and the target. TU is the target and the input. So here you can see here we implement the training loop. We have our parameters, that is what is params, meaning W and B. And now we calculate the model. So here is the model. Given the input, the model, we calculate the prediction. So here is the model that will calculate prediction. This is TP is prediction. So here it means we have this guy, the prediction. Now what we need to do, since we have the prediction, I'm gonna the true target. Same we find in the difference using loss function. So this is calling the loss. Can you see that loss function? Given the prediction and the true value, we find the loss. So when someone finding the loss, this score is this guy, but we need to update these weights. How do we update this weight? This is what we talk about using this gradient descent, which is something that we may need to look at and understand. Then this gradient descent is implemented this way. This is the gradient function. Can you see that? So this gradient function is basically what we show here. That is what it's doing here. But analytically, so this is the guy. So this is the guy. So this grade, when we do this grade, it means when we calculate this guy, given our input, given our this, and given the weight, it will update. What these guys do is it will update these values. It will update your weight, your parameters. So gradient descent will update your parameters. This means that we will have a new. This means that we will have we have a loss, and now we say, okay, this loss is very large. How can we update this weight so that when we do another prediction, the loss is low? Then we need to reduce, change this weight. So this guy, the gradient function that we call here, changes this weight. That is update this weights, right? So when we update this weight, we have we need to update our parameters for the next iteration. Then how can we update our next parameters? We set the parameter minus learning rate times gradient, which is this. Can you see it? As I showed. Parameter minus learning rate times gradient, right? parameter minus line rate times gradient. And yeah, so this is basically what is learning doing. This is, I know it's a little bit messy and also maybe confusing, but if you don't understand this, it's totally fine. The next session will show us how Pytorch abstract all this. They are doing this to give an intuition what is really happening behind the loop, behind the scene. But it's not necessary to even completely understand this. But we are trying to build the mathematical understanding of that. So you can see now here the parameters now, because remember, these params is the initial weight we give. Can you see the W and B initial weight? So we need to update it to go to the next loop so that we reduce the loss, right? So you can see here, this weight, we need to update. This is the weight, we update, weight update. So what is doing with the weight update? This is gradient. So here we update the weight parameter, the original, minus linear rate times gradient. And now here we print. So let's show this guy what is happening. And this is the complete training loss. So this is the same what we show here. So if you look at this guy, given everything here, this is what we call forward pass, right? In our line, going through this is called forward pass. So this is forward pass. Yeah, okay. This is what I showed earlier. So now let's look at how we can do that. So you can see here we create the function. The function is called training loop. Training loop. That is the name of the function. Is called training loop. So when you create your function, now what you need to do? Yes, yes.
My question is,
yes.
This gradient descent algorithm, is it doing the back propagation?
Yeah. Yes, exactly. Okay. Good question. Maybe I don't explain this. So gradient descent is what is actually doing what we call maybe. So here you can see from here, we are doing what is called back propagation to update this weight. So gradient descent is what is doing this update stuff. So, but we'll come to that in a little bit as well. Yeah, that's a good question. So here we can see our training loop. If you want to train, you give your number of epoch you want to do cycle 100. Learning rate is this guy. You give some values, parameters. You give the parameters 1 and 0.0. This is our W and B initial parameters, and this is your value TU and TC, which are the ground truths and the target. So you can see this is a training loop, and we can train our model and try to see what is the loss, what is the error. So we can see here we have, we put some stuff and do some output, which will print the parameters and gradient and stuff like that. So here that is what is printing, parameter and gradient. We can see it in the first epoch, in the second epoch, in the third epoch. You can see in each epoch, given this parameter and given the gradient, grad, look at the loss. In the second epoch, given this param, given this, look at the loss. We can see that given this, okay, epoch 3, can you see that? So up to the end, but this is actually at you can see at epoch 11, the loss goes infinite, so it cannot continue. So you can see what happened. Our training process literally blew up, leading to loss becoming infinite. So there is some issue. This is a clear sign that parameter is ripping up the too large and their value start oscillating. So this is a problem, Hajia, that you asked, that the weight may go somewhere randomly when we initialize them. So when we initialize our weight randomly, then we may have problem. So you can see here, the weight may come to here this way, very large value, or go this value, and now we will have oscillating. So we should initialize our weight maybe to be some reasonably small and some stuff like that. Can you see that? And now we will not be oscillating. But if we do some kind of initialization, we'll have what is called divergent. So our function will not converge, it will give divergent. But what is the solution? By limiting the magnitude of linear rate times gradient by simply choosing smaller linear rate. So one way is to choose small linear rate. So you can see here the linear rate we use, this is 10:2. So we choose smaller one, that is 10:4 is smaller, but 10 raised to power minus 4 is smaller than 10:2. So when we choose the smaller linear rate 10:2, we can see that we epoch 100 epochs. Can you see that? And we can see that this behavior is now stable, but there is another problem. The object of parameter are very small. So what this is telling us is this: you can see you can see, so we can see now we can choose to the line rate 12, but the behavior now is stable, but there is another problem. The object parameters are very small, so the loss decrease very slowly. So look at what we mean by this, right? So you can see this one, what is the loss? 1763, right? But the loss here is 323, the loss is 78, but what about here? At epoch is 30, look at the loss, 229, 105, 29, at 11 is 29, at epoch 99 is still 29, at epoch 100 is still 29. So it means the loss, so it's decreasing 2.3, can you see 2.2? But the effort, the loss is decreasing very, very, very slow. So what is the solution? So the solution is by making learning rate adaptive. So that is what we call adaptive learning rate. What this means is that if we look at this guy, we can see that we have two parameters, right? But we can see the gradient here. This, look at the value of this gradient, 4513. Look at the value of this gradient, 82. That is the gradient of this one, this. The gradient of this parameter is this. You can see the gradient is very diverge, right? It's not close. Then it means we are using one learning rate to move from direction of this and to move. We are using the same learning rate, but if we are using the same learning rate, we will move to different direction because these values are large. So can we use a better approach that if the gradient is large, we use a learning rate that corresponds to the largeness? If the gradient is, we use a learning rate that corresponds to this. That is the notion what we call adaptive learning rate. So what is the solution? We could solve this by making learning rate adaptive. That is change according to the magnitude of the object and their optimizer scheme. So change according to the magnitude, right? So if the gradient is large, use the learning rate very large. If the gradient is small, right? So this means that we are going to use two learning rates in this scenario, right? Because if it is large for anyone, so this is the solution. That optimization technique like SGD gradient descent need to set a hyperparameter learning rate before training the model. Yeah, we set the learning rate here. Can you see the learning rate? But the problem is we need to update this learning rate manually each time. Can we have a better intelligent way that will try to set the automatically adapt the learning rate? If the gradient is large, it will use large. That is what we call the notion of adaptive learning rate, which like ADA grad, ADA delta. These are called adaptive optimization techniques. So instead of using gradient descent, SGD, mini batch, these are not adaptive. They don't adapt based on the gradient that we use. So the best way we find is actually to use adaptive learning rate, and they will solve the problem. But another issue is normalizing the input. So I think I have, okay, I'm sorry I'm taking much time, but I think this is worthwhile trying for us to build the notion. Another issue is normalizing the input. Remember we said when you have data set, you want to do machine learning. And if this input, your features, they are of different scale, you will not have a good machine learning, right? Training. What the problem we can see that first epoch gradient for the weight is 50 times larger than the gradient for bias. Let's look at that. Is a problem I'm taking. Yeah, look at the gradient 4517. The gradient for the weight, the gradient for the bias. This gradient is 50 times than this. What causes this? What causes this? The problem here is that our values, our input value, that is TU and TC, they are of different scale. Let's look what will happen. Is happening. Let me show us something. Sorry. So let me show something like this. Oh. Okay. This is our TU. This is our TC. Right. Look at the TU. Can you see 35, 55, 68, 48? Look at TC. Look at 0.5, 14. Can you see that? 11. You can see they are of different scale, right? So what we need to do is we need to put these guys into the same, oh, sorry, not this guy. TU, I mean, sorry. Yeah, TU. What I mean by this is that here we have the values are of different scale. Can you see we have what is the minimum value here? The minimum is 33. What is the largest value here is 8, right? It means the values are of different scale. So we need to do what is called normalization. If you remember in my machine learning, I tried to give this example in our machine learning class that, for example, if we have in Kano, we want to predict how wealthy people are. Idan misali yanzu sai ka dauko Mr. X, Mr. P, sai kuma ka dauko Dangote. Mr. X yana da kudin sa 100 yake da ita a banki. Mr. B has kudin sa 30 yake da banki. Sai kuma ka dauko Dangote. Ka gwamutsa. Sai ka ce kana so ka predicting din how wealthy people are. Kuma ka dauko Isiyaka Rabiu. To kaga ai you cannot predict well, right? It will always be biased toward the Dangote and Isiyaka Rabiu because they have more money, it's not the billions of naira. So what you can do is ka ɗauko mutane masu kuɗi iri ɗaya daidai misali wanda yake 10,000, 9,000, 8,000, 10,500, then you train your model a waɗannan mutanen, then you can try to predict. So that's why here our value also here, because it's not stable, we need to normalize it to become stuff like that. In that case, if we normalize, then our gradient here will be close in every situation. So let's look at what we do. How can we do normalization? One way to do this kind of normalization is just to multiply by some numbers, right? So this is what they are saying. We can see that the first epoch gradient of the weight is about this. In this case, a learning rate that is large enough to mingle update one will also be large to be used unusable for the other. So you can see here, the learning rate we can use to update this P, to update weight with this gradient will not be usable akan wannan saboda anan zamu amfani da big learning rate amma kuma anan ba zai yi amfani ba saboda muna da gradient very small. So in that case, that's what they are saying. If this is a learning rate that is large enough to meaningfully update one will be unusable for other, and a rate that is appropriate for other won't be. We could have individual learning rate for each parameter, but for model with so what they are saying, you can have individual learning rate for each other, but one number is not a perfect solution. One way is to normalize the data. How can we normalize the data? We can use small value, 0.1, and multiply each value here. So when we multiply each value here, it will become in some kind. So here you can see we have 2u, but here we have 2u. Un means no. We normalize it. Let me show us the result now. On, can you see a 2u on? Can you see now it's 3.5, 5. Can you see 8? Can you see them? Can you see? So you can see these values, they are within some kind of reasonable range, right? So if they are within the reasonable range, then let's train the model now with this 2un. So here you can see our tu. We are substituting tu, we update with the normalized. Tun means normalized. Now let's train the model now here. The loop, when we train, look at the, can you see -77, -10? Can you see the gradient? Can you see the gradient minus this? So in this case, it means the gradient will actually at the end, look at the gradient here, minus this. So what this is telling us that the gradient will not shoot as the way we have this, it shoot far behind the this guy. Can you see the difference between this guy? So what they are saying is that normalizing your data is very important even in deep learning. But as we will see in the next sessions, some other optimization algorithm we'll see like Adam, they don't actually care about normalizing your data. So yeah, so that is okay. What they are saying. Okay, for larger, more sophisticated normalization and easy and effective to improve convergence. So now let's improve our model with 500 epochs, and now we see this guy. Okay, now we can see this guy. We don't print our parameters now here. We can see epoch 1, this is a loss. You can see our loss is decreasing. We up to this. So this is our final weight update. So you can see we have now our weight, the new update weight that will make our model to fit perfectly weight. These are the way. So as I said, the main aim of training a model is to find a weight that will optimize your loss function. So here, these are the weight when we finish training the model. This is the weight, the blue, this is the B, your bias, these are the ones that will optimize your way. So good, our loss decreases while we change the parameter along the direction of gradient. Yes, our loss, we can see decrease. It does not go exactly to 0, but we can see the loss does not go exactly to 0 because there are some issues. So ideally, we want our loss to become 0, but there is a 0. But what we want some kind of tolerable value. We want to decrease it. You can see from the beginning, what is the loss? 80, right? So you can see here, we have this loss. So this means that when you are doing deep learning, you are not always perfectly trying to find the loss to be 0. For example, in this case, you can see if you train on finally, you still have some error. Maybe you could add there. So you can see you still have an error, but it's not as terrible as maybe error like this. So this is basically the main idea. Yeah, okay. Yeah. So yeah, so you can see it does not go exactly to 0. This could mean that there are enough iteration. So if it does not go to 0, there are a lot of possibility. Meaning, number one, you don't have enough of iteration. Maybe now we have 500. If we do 1,000, the loss will continue to go low, or that the data point sit exactly online. And as we our measurement, okay, and another scenario is that your measurement is not perfect, so you may not exactly have your loss to be 0. So yeah, that is basically the boring part of this, and I hope we built our intuition on how the learning works. The subsequent section, that is these sections, will actually be better straightforward, just calling the functions to do all this stuff. But anyone wants to add something before we go to, I don't know if we can go to the next session or we do them tomorrow, but what anyone want to add something or question? Yeah, go ahead now.
Okay, actually, Shamsu,
yes, Haja.
actually, during, I don't know, it's just a comparison. During all my experience, I came to realize that my loss is mostly 3 and 2. And I get worried, why is it that my loss is not 0? After all, I read and I saw that mostly loss is 0. So now I don't have anything to be worried about. Is that what you are saying?
Exactly. So 2 things. If your loss is not 0, I will be simple. 1, you have not trained your model large, I mean, with number of a lot of iterations. Okay, let me show you. So here you can see we have 5 iteration, right? Epoch. Look at 0.94. Let's look at the other guy. This guy, we use 100, right? Number of epoch. What is the loss? Look at the loss. Can you see it? Yeah. 22. So the market company the loss number of iteration epoch go 30. Can you see your loss is 22? Among the market company the number of iteration that do we are may loss gumu.
Yeah, it's 2.
May loss gumu.
It's 2. Yeah.
So one thing, if you are lost is 0, but one thing is you have not used maybe increasing the number of epoch will try to do. That is one thing. Number 2 is there is no perfect, there is noisy in your data that the model cannot learn perfectly. For example, you have you annotate your data. This is positive, this is negative, this is positive. But I actually there are wonder positive ne amma wajen annotated sun saka negative. To shi ko model why it goes yana ta learning din positive. Wannan din nan fa ya sun sa mashi negative will learn it as negative, so zai dan confuse, so da akwai noise, so bai lalle ne ya je perfect abun ba. Amma idan experiment is perfect, then the loss will definitely go to 0.
Okay.
Yes. Yeah, anyone want to add something?
But are there models that will have loss of 0?
What do you say?
Real life models that can have a loss of 0.
No. That is so the real life data set is noisy. That is just a fact.
Yes. Yeah.
In real life, our data is noisy. Yes, it's not linear. Yes, it's not perfect. To muka mu mutane muka mu ai ba perfect muke ba ballanta na kuma data.
So the target yawanci dama is just to get as low as possible in the loss value.
The data generated is actually us that are generating the data itself. So
exactly.
Is there a borderline? Is there any borderline? Maybe you say maybe from so number is okay.
No, I'm not sure. Maybe we can see. So, but there is something we'll see in the next. Let me quickly go through the next session. And we see what I was saying. Please forgive me. But energy, I'll quickly go through it. What do you think? Can I quickly go through it? Next week and the chapter. What do you think?
We did not read through it, so we don't, most of us.
Okay, so can you mean we can stop here and do this section tomorrow, Ko?
Yeah, we don't know.
Okay. Yeah, so sorry, Dr. Ibrahim kai da kai chapter next week da kai ta gobe gashi kuma ni yau bayani nayi ina ta bayani da yawa. But I think it's good to build the intuition. This chapter is basically trying for us to build up the intuition. The subsequent chapters, don't worry if you don't understand this, like we are doing some kind of manual step, but this is just trying to build the intuition, how learn works. The next chapter and this is just calling some function just to show us, okay, abunda muke a can wajen ai ga kai abunda zaka kirawo. You will do that. You don't need to do some kind of manual gradient or calculate the gradient and stuff like that, right? Yeah. So Inaji, anyone want to add something based on what you go, because we are already on top of the time, and tomorrow we will complete the chapter, and the next week we can do chapter 6. Anyone want to add something? Okay, right. Okay, so I think we are good. We can see that what you always look at is your loss decreasing? Idan loss ɗinka baya decreasing, then back learning. Look at it, the loss is 80, 37, 30, 29, 20. If it is decreasing, then you are good. Yeah, while you are changing your, that is the aim. The aim is change the parameters and the loss will be decreasing. That is basically the aim. That is, we are learning. So yeah, I love this guy. So always change this weight and find the loss code. If loss code kana changeawa, loss code ɗinka yana raguwa, then you are good. Keep changing the weight. Keep changing until you reach a reasonable loss score. Then you are good. Yeah, anyone want to add something? Tunde, Rabiu, Saadatu, Sahih, Zaradin, Idris, Murjam, Ibrahim, Amina. Yeah, anyone want to add something before we go? So tomorrow will be like the real Gongwan things, how deep learning work, how Pytorch work. So tomorrow we'll see Pytorch autograd, back propagating all things. So we will see what is called Pytorch autograd, which is automatic differentiation engine of neural network. So yeah. So I think if you have not read this chapter, please read this chapter before tomorrow. Then the munzo munai, you'll be getting it. Yeah, read this chapter before tomorrow so that the moment munzo, you may have a lot of questions to ask and you may have a lot of things to contribute. Some of us was current chapter bio shi sa ba sa contributing.
Dr. Shamsu, za mu yi kokari makaranta amma ka san yanda Najeriya take ne, no work no pay ga family abin ne yayi sai godiya ubangiji.
Sai godiya ko?
Wallahi.
Ga Allah sa, yeah. But I think yeah, the good thing is when we don't read, we can listen, that is more confused and you will not get a lot out of it. But when we come, like when we read, we come as discussion one age. One age, we'll be putting more ideas and we learn together. And yeah, I mean, yeah,